Okay, let's talk about chapter 11. Hopefully you've read it, but let's go over some questions from it. Just starting at the first page, the most important aspect of the randomness in games of chance, they have to be fair. You can read this here. Fairness is made up of the fact that you can't guess the outcome, and all possible outcomes are equally likely. Those two things are essential to fairness. Do random outcomes have structure? Even if so, give an example. We're sort of tempted to say that randomness sort of goes on forever or whatever. But let's say if you use a random number generator to generate numbers, okay? Now, if you generate 10 numbers, it would be very unlikely that those 10 numbers would consist of 0 through 9. 10 single-digit numbers. So let's say you generate just 10 single-digit numbers. It's very unlikely you would get 0 through 9 and no repeats. But if you generate 1,000,000 single-digit random numbers, it's very likely that you would have close to 100,000 zeros and 100,000 ones, etc., through 100,000 nines. Now, you wouldn't have exactly 100,000. You'd be a little bit above or a little bit below. But you would see the structure emerging, a uniformity. Same thing if you made many rolls of dice. You'd get the proportions would be 1 out of 6. You would have same thing if flipping a coin. You'd be half heads, half tails. After many, many trials. So anyway, there is a structure to random outcomes, but it only emerges after many, many outcomes. Now, what number did you pick at the top of the page? Whether you picked 3 or not, 3 is the most number picked. So in other words, there was 4 numbers at the top of the page, and people in general do not pick these equally. So what's the meaning of this? What it means is that humans are not a good source of random selection. Humans are by nature biased. I mean, bias is not bad. Bias is an outcome of our experience and our intuition. And it's at the heart of the things like, the accusations of racial profiling by police and that sort of thing. And then the counterattack is, people have different reasons or the experiences or whatever upon which they base their decisions. But anyway, humans are not a good source of random selection. Humans are by nature biased. Random numbers generated by a computer program are called pseudo-random numbers, and are they okay to use? They're certainly fine for what their purposes that we want to use them for, which is to use them to generate data. Now, why do we want to do this? Well, for a couple different reasons. The main thing is we may have the question about how often something occurs, and it might have to do with a situation which is difficult to simulate, or difficult to repeat, or expensive. Let's say we do an experiment with, somebody has a theory that swimming with dolphins helps people with depression. So we get 30 people together and fly them down at great expense to somewhere where they can swim with dolphins. We split them up into 2 groups. Let's say the people are selected randomly. We randomly select them to swim with dolphins. 15 swim with dolphins, 15 don't. Everybody has the same experiences otherwise. And then we count how many people, had their depression relieved. If we want to evaluate, we want to see how significant our results are. It would be very difficult. We'd have to do this over and over again in order to see, well, do the results? Do we expect these results or whatever? With simulation, we could simulate that event many, many times over and then evaluate its significance in light of those simulations. So simulations are actually really important, really useful in situations where it's impractical to replicate a particular experiment over and over again. So that kind of answers the question 9. Now, what is the answer to one simulated question? Okay, well, the simulate question, the question is what you're interested in. Okay, what you want to know about. Like in the case in the book, they're talking about the question is, how many boxes of cereal do I have to open in order to get all 3 of the famous athletes? Now, let's see, I think there's Tiger Woods and Serena Williams, and I forget who the third, Beckham, or some soccer player. Anyway, so how many boxes of cereal? So that's the question. Okay, now we don't want to open thousands of boxes of cereal. On the other hand, we do have proportions that were given to us by the company. We'll talk about that in a minute. So what is the basic building block of a simulation called? That's called a component. Now in this case of trying to answer the question of how many boxes of cereal do I have to open to get these pictures of these 3 famous athletes, the component is opening a box of cereal. So that's the basic building block of the simulation. And what is a trial outcome is called the response variable. Now, what is the response variable? In this case, it would be how many boxes of cereal I had to open in order to get all 3 athletes. Now, let's take a look at the book, and we'll continue from there. So let's summarize what we've had so far. Okay, so we have a simulation question. In this case, how many boxes of cereal do we have to open in order to get all 3 athletes? And we have a component of the simulation, which is opening a box of cereal. Every time we open enough boxes of cereal in order to get all 3 athletes, we have conducted a trial. So we have the simulation question, we have the component, we get enough components together to answer the question, then we have a trial, and then we have the response variable, which in this case is how many boxes of cereal we had to open. So in other words, how many components were in the trial in order to get all 3 athletes. Obviously, the minimum would be 3, potentially. The number of boxes, could be quite large. Okay, so how do we model a component outcome? First of all, identify the component that is the fundamental action to be repeated. In this case, our component is the opening of a box of cereal. Now, the second thing, this is really important. Explain how you will model the component's outcome. We're told 20% of the boxes contain the picture of Tiger Woods. And 30% contain David Beckham and 50% have Serena Williams. So that breaks down to 0.2, 0.3, and 0.5. So we only need 1 digit to model this 20%, 30%, and 50%. If it was 22% and 18% and 50%, whatever, then we would need 2 digits. Okay, so we're only going to use 1 digit, so we're going to use the digits 0 through 9. Now we don't do 1 through 10. If we do 1 through 10, then we'll be using 2 digits for number 10. We only want to use 1 digit. So 0 and 1, we're going to say, is Tiger Woods. So any random digit we come across, which represents a single random digit that represents opening 1 box of cereal. If it's 0 or 1, we've opened a box for Tiger Woods. There's Tiger Woods in it. If we get a 2, 3, or 4 in our series of random numbers, we've gotten a David Beckham. And a 5 through 9 is Serena Williams. Now, explain how you will combine the components to model a trial. Remember, a trial in this case is opening up boxes of cereal until we get all 3 athletes. We pretend to open boxes, repeat the component, that is, just go from number to number, until our collection is complete. We do that by looking at each random digit and indicating what picture represents. We continue until we found all three. State clearly what the response variable is. This is what we're interested in. We want to find out the number of boxes it might take to get all three pictures. Now we run a simulation, run several trials. Okay. Now let's look. Here's a line of random digits produced by a random number generator and printed in the book here. Okay, so the first number is an 8. Now remember, we're doing one digit at a time. Okay, now an 8 falls in the range of Serena Williams. So this 8 right here is the first box of cereal that we opened. We got a Serena Williams. Now notice the next box is also Serena Williams. So we still have only one of our pictures, but we've opened 2 boxes of cereal. The 0, well, that's a Tiger Woods. We now have 2 out of 3 of the people that we want. Okay, but we have opened 3 boxes of cereal. Number 6. Okay, so this is our 4th box of cereal, and that's Serena Williams. That's our 3rd Serena Williams, and we've got to keep opening boxes of cereal until we get all 3 of the athletes. So far we've opened 4 boxes. Now number 4 is David Beckham. So we now have Serena Williams. Actually, we have 3 Serena Williams, 1 Tiger Woods, and a David Beckham. And our trial is over because we now have all 3 pictures. Now, the response variable is 5. We opened 5 boxes of cereal in order to get our 3 athletes. And the trial ends right here. And you would draw a little line here or something like that, and then continue on to the next trial. Now, you do not skip numbers. Unless you've decided ahead of time there are numbers that don't apply or whatever, and we'll talk about that later. But right now, in order to keep things truly random, then you have to continue on to the next number. So the trial 2, we get a number 2. Okay, that's David Beckham. So we now have 1 David Beckham in our second trial. Number 7, that's a Williams. So now we have we have a Beckham and a Serena Williams. Now we get a 3. That's another Beckham. We've opened 3 boxes of cereal, and we have 2 Beckhams and 1 Serena Williams. A 2, a 7, and a 3. The 4th box of cereal is a 0, and that's Tiger Woods. So our second trial took us, let's see, 2, 7, 3, 0. 4 boxes of cereal. So the response variable is 4. So we now have 2 trials with the response variable 5 and a response variable 4, and so on. And we could go on as long as time permitted, making these simulations. Okay, let's just review it on the next page, and notice that they do many trials here. They do all the way up to 9, and they just keep going. Notice the 5th trial, which we only did the first 2 trials. The 3rd one took 7 boxes. The 4th took 5. But the 5th took 18 boxes. Now, this is not caused by a store, being full of one particular kind of box or whatever. This is random number generation. This is completely a simulation. So even with random numbers and simulations, you're going to get these unusual occurrences. Random does not mean regular or evenly distributed. In fact, random number behavior is going to involve streakiness, clumps of numbers, and so on. When humans try to make numbers themselves that look random, they often get into trouble doing that. And we will talk about that next week. The LIBOR interest rate fixing scandal, which is a huge scandal involving billions or possibly even trillions of dollars in expropriated money, was detected by the fact that the fixed rates set were not random enough, by a method of detection that was developed well over 100 years ago. We'll talk about that next week. Okay, so we collected and summarized the results of all the trials. And right, we got a shape, center, and spread, and all of that. If it's that state your conclusion. And in this case, the results are definitely going to be skewed, right? The smallest number of boxes is 3, but it can get quite big. So we'd use the mode to describe this distribution. In the IQR, we definitely would not use a mean and standard deviation. Now they talk about how many trials would you actually want to run. Well, 20 is, but if you use a computer or a calculator, or whatever, you can run hundreds or thousands or millions, and that's much better. Now, this example is kind of interesting here, but I'd like to turn the page and get on. You could look this over yourself, and let's go to this just checking. Now I want to set up the page here a little bit to talk about this example, and I'd like you to work on this a little bit. But let me stop this for a second first. I want to pause. Okay, now here's the situation. Does the team with the home team advantage, with home field advantage, tend to win the World Series more often than not? So we have to read this kind of carefully here. So the World Series consists up to 7 games. First team to win 4 games. So the sequence of games is 2. Let me get this black. 2 at home, 3 away, and then 2 back at home if they're necessary. Now, in general, the team playing at home, whether they're the team with the home field advantage or not, has a tendency to win. Probability of 0.55 of winning, 55% chance of winning. Which means, so this is whoever is at home. Okay? So the home team is a 55% chance of winning the first 2 games. For game 1, 55% chance of winning game 2. Now when you go to the other stadium, now you're at the team that didn't. You're at the stadium of the team that did not have the home field advantage, but now the odds switch in their favor. In other words, whatever team is home, they have the advantage of a slightly greater proportion of winning. So once it switches, then the team that did not have the home field advantage now has a 0.55 chance of winning for those next 3 games. Then it switches back to the stadium of the team that did have the home field advantage, and then that team now has 0.55 advantage. So let's talk about this. Let's say the Cubs are playing the Sox in the World Series, and the Cubs, because the National League won the All-Star game, which is how the home field advantage is set, the Cubs have the home field advantage. So the first 2 games are played in Wrigley Field, the next 3 games in Comiskey, and the last 2 games in Wrigley Field. So what's the question we want to know? We want to know, did the team with the home field advantage win the World Series? That is, the team that started out at home and that altogether has 4 games at home and the other team has 3 games at home. Does that team tend to win the World Series more? Okay. So that's the setup. So what's the component to be repeated? Well, the component to be repeated is 1 game. Winning or losing 1 game. Okay, 2. How do you model each component? Well, we got 55 and 45 adding up to 100. So we're going to need 2 digits. But notice this, we're going to use 2 digits for each number. So we're going to go from 00 to 54. That's 55 numbers to represent winning at home. And 55 to 99, the visiting team winning. Okay? So 00 to 54. Now we have to use 2 zeros because each number, in order to use the probability table properly, then we need each number to be 2 digits, even if it's 1 through 9. So we got 00 to 54 and then 55 to 99. All right. And this is winning at home. And this is the home team winning. This is the away team. Now, we're not talking about the team with the home field advantage. That's fixed. But whether you're home or away, that varies depending on the first two games are at the home field of the team with the home field advantage. That's the Cubs in this case. The next three games are going to be at Comiskey Park. The Sox will be at home. Okay, they'll have the 55% chance of winning. Now remember, the Sox do not have the home field advantage. They started out, the World Series started at Wrigley Field. All right, so 3. How will you model a trial by combining components? Okay, the trial is win 4 games by the same team. That's the end of the World Series. Okay, somebody has to win 4 games out of 7. One single team has to. Okay, what is the response variable for whether the team with the home field advantage won the World Series? In this case, did the Cubs win? Because the Cubs are the team with the home field advantage. And so in every trial that we run, we are going to see whether or not the Cubs win. And how will you analyze it? We'll see how many times the Cubs won out of how many trials. So if they win every time, then we'll do, like, let's say we do 100 trials, and it'll be 100 over 100. Or they win 80 times, 80 over 100. That's how we're going to analyze it. Okay, so we'll take proportions. Now, where we get our random numbers from? That's a good question. So we're going to look in your index for your book, and you want to go to appendixes here. That's formulas. I didn't want appendix. I want appendixes. Right here. I gotta use my mouse. There we go. Here, okay, I'm sorry, under appendixes is G for tables. Okay, so here's the table we're going to use with the random numbers on it. Now, I'm going to make this a little bit bigger so we can just see the first row a little bit easier. Okay, so here we're going to start with row 1. And let me move this up a little bit, just so it's a little easier. I can move these around. Okay. So we'll start with row 1 and go from left to right. Now remember, we're taking 2 digits at a time. And we're saying 00 to 54 is winning at home, and 55 to 99 is the home team wins, and 55 to 99 the away team wins. Now we're not talking about the team with the home, just with the home field advantage. We're just saying whoever is at home. All right. So the first number is 96. Okay, now they're playing at Wrigley Field. The Cubs have the home field advantage for the World Series. It's a number 96, so the Sox won that game. Why? Because it's 55 to 99. The visiting team wins. Okay, the next number is 29. Okay, 29. That's within the range for the home, so the Cubs win that game. Now, these first 2 games were at Wrigley Field. The next 3 games will be at Comiskey Park. So where the Sox will be at home and the Cubs will be away. Okay. So we've used 96 and 29. The next number, notice that we got to jump this gap here, is 90. Okay, 90. We're at Comiskey Park. And who won that game? Well, the visiting team won, so the Cubs win. This is CO, Comiskey Park. Okay, the Cubs won that game because now they're visitors. Okay, now the next number is 7-1. That's also a win for the visiting team. The Cubs win again. Okay, the third number is 96. That's also a win for the visiting team. Okay, now that's a total of 4 wins for the Cubs. They've won the World Series, and that's the end of the trial. Now, we don't care how many games the World Series lasted. All we care about is, did the Cubs win, yes or no? So the end of that, so trial 1, we could have a table here, okay, so, is the Cubs win. And we could keep a tally somewhere for Cubs winning or whatever. Let's see. Cubs and Sox. Okay. So the Cubs won a World Series. Okay. And now we would continue from 96 and we start our next simulation at 98. Okay. So 98. That's also a victory for the Sox. Remember, now it's a new World Series. We're starting back at Wrigley Field. 64. That's a victory for the Sox. They were at Wrigley Field. They were the visiting team, and they won both of those games at Wrigley. Okay, the next game is a 22. Okay, now the Sox are the home team. So they won that game as well. They won the first 3 games. Okay? So let's review. 98, 64, those are wins by the Sox as visitors to Wrigley Field. The 22 is a win by the Sox as the home team at Comiskey Park. And then finally, 06. A win at home for the Sox. It's a sweep. They win in 4 games. And so the response variable is the home team did not win. Okay, so we've won 2 trials. And the team with the home field advantage, the team that started out at home, has won once. And so we would continue to do these simulations. And let's say I had you do 10 or whatever. Or you were asked to do 10. And so that's how you do a simulation with a number table. And it's important that you know how to do this. Now, that's about it for the introduction to this. Spend the rest of the time what you have working on your homework problems or are working through the rest of the chapter.